A single sugar cube could hold the weight of Mount Everest. This is not science fiction, but the reality of a neutron star, where matter endures pressures so extreme they shred the very rules of physics. By the end of this journey, you will understand what happens to the universe's fundamental building blocks when they are pushed beyond any conceivable limit. We will venture into stellar cores where atoms are crushed into exotic soups and confront the possibility of matter dissolving into pure quark energy. How do you picture the absolute limits of reality? This stellar forge operates on an almost unimaginable scale. Picture a star not like our own sun, but a true giant, perhaps 20 times more massive. For millions of years, it burns through its nuclear fuel, fusing hydrogen into helium, then helium into carbon, and so on, creating progressively heavier elements in its core like a layered cosmic onion. Each layer of fusion provides a temporary outward pressure, fighting a constant war against the star's own inward pull of gravity. But this battle has a final, inevitable end. When the core finally fuses its last atoms into iron, the fight is over. Iron is ash. It cannot be fused to release more energy. In that instant, the outward pressure from nuclear fusion vanishes. And gravity, after waiting for eons, wins. The core, which may be larger than our entire planet, collapses. It does not fall slowly. It implodes at nearly 1/4 the speed of light, compressing into a sphere just a few dozen kilometers across in a single, breathtaking second. The forces at play here are so immense that they rewrite the very structure of the atoms themselves. The empty space that makes up over 99% of an atom is brutally squeezed out. Electrons with their negative charge are rammed directly into protons, which carry a positive charge. In this ultimate act of cosmic alchemy, their charges cancel out and they merge, transforming into a neutron. A single neutral particle, a star that was once a brilliant ball of incandescent plasma, is in its final moments reduced to a seething, ultra-dense sphere of pure neutrons. This transformation releases a ghostly tsunami of particles called neutrinos, which carry away an almost unimaginable amount of energy. The shockwave from this rebirth blasts the star's outer layers into the void in a supernova explosion so bright it can outshine an entire galaxy. And what remains in the heart of that expanding cloud of stellar debris is the newborn neutron star, a city-sized cinder of the most extreme matter in the known universe. That newborn cinder of a star is far from dead. It spins, and it spins with a ferocity that defies belief. A star that was once massive enough to swallow planets whole now completes entire rotations in mere fractions of a second. This furious spin, combined with a magnetic field trillions of times stronger than Earth's, transforms the neutron star into something else entirely, a cosmic lighthouse known as a pulsar. From its magnetic poles, it fires out focused beams of radiation, powerful torrents of radio waves, X-rays, and gamma rays. And as the star whirls, these beams sweep through the darkness of space like the blinding beam from a lighthouse on a distant shore. If that beam happens to flick across our planet as it rotates, our telescopes register it as a pulse that comes with a regularity so precise it rivals the best atomic clocks we can build. The discovery of the first pulsar in 1967 sent shockwaves through the scientific community. The signal was so unnervingly regular that astronomers half-joked it might be a beacon from an advanced alien civilization, earning it the playful nickname Little Green Men 1. But the truth was, if anything, even more extraordinary. They had found the first direct proof of a neutron star, a celestial object that had until then existed only in theory. This was the moment astrophysics truly opened a window into the most extreme conditions in the universe. The steady, metronomic ticking we detect from these objects is a complete illusion, a mask over the chaotic violence at its heart. That perfect rhythm emanates from a maelstrom of crushed matter, gravitational forces that can tear space itself, and magnetic fields so intense they could strip the information from every credit card on Earth from a distance of 100,000 kilometers. Each pulse is a signal from the edge of what is possible, a fleeting glimpse into a realm where matter is pressed into forms we are still struggling to comprehend. Beneath the steady pulse of the cosmic lighthouse lies a surface more alien than any desert or ocean. This is the neutron star's crust, a crystalline shield of immense strength. Imagine a layer about a kilometer thick, but do not picture soil or rock. This crust is a rigid lattice, a perfect, unyielding grid of atomic nuclei, mostly iron and elements far heavier, all crammed together under gravitational pressures that dwarf anything in our solar system. The empty space that defines a normal atom is completely eradicated here. The nuclei are pressed shoulder to shoulder, trapped within a swirling quantum sea of free electrons. This creates a material with a density so staggering that a single sugar cube-sized fragment would weigh billions of tons on Earth. It is the strongest solid in the known universe, a substance that makes diamond seem as soft as butter. And yet, this perfect crystal is under constant, unimaginable strain. The star's insane rotation and its powerful magnetic fields exert tremendous stress on this rigid shell. Sometimes the crust cannot take it. It cracks. These events are known as Starquakes. A single shift in this crystalline landscape can release more energy than every solar flare our sun will ever produce throughout its entire multi-billion-year life. These cosmic tremors ripple through the star, causing tiny, detectable changes in the spin of pulsars. For scientists, these glitches are like listening to the creaks and groans of a colossal structure, providing our only direct clues about the incredible rigidity hidden deep within this stellar corpse. The crust is a testament to the fact that even in death, a star is a place of violent activity, its solid surface a fragile mask over the even greater strangeness below. But that solid crust is merely the thin, brittle shell of a much deeper mystery. Beneath it lies the outer core, a realm where the familiar laws of physics are not just bent, but utterly rewritten. Here, the crushing weight is so immense that even those densely packed atomic nuclei can no longer hold their structure. They dissolve. The protons and neutrons, once neatly arranged inside their nuclear homes, are set free into a bizarre quantum sea. This ocean is not made of water, but of a substance known as a neutron superfluid. A superfluid is a state of matter with properties that seem like pure magic. It has zero friction, meaning it can flow forever without slowing down. If you were to stir a cup of this superfluid, it would never stop swirling. It can creep up the sides of its container and drip out, seemingly defying gravity itself. These are quantum behaviors usually only seen in the tiny world of atoms, but here they are playing out on a colossal, stellar scale. This churning, frictionless ocean is the engine behind the starquakes and spin glitches we can detect from Earth. Think of the star's rigid crust spinning at one rate, and beneath it, this superfluid spinning just a bit faster. They are not perfectly locked together. The superfluid contains tiny, tornado-like whirlpools called vortices. Normally, these vortices are pinned, held in place by the crust's crystal structure. But when the stress becomes too great, they suddenly unpin and surge outward. This transfers a massive jolt of rotational energy to the crust, much like a figure skater pulling their arms in to spin faster. In an instant, the entire star experiences a glitch. its rotation speeding up by a tiny but measurable fraction. That steady, metronomic pulse from the pulsar suddenly jumps. Each of these events is a direct message from this inner quantum chaos, a sign of the frictionless storm raging just beneath the star's unyielding surface. Yet even that churning quantum ocean is not the final frontier. Deeper still, beneath the superfluid, lies the true heart of the mystery, the inner core. This is the ultimate sanctum of the neutron star, a place where conditions become so extreme that our current understanding of physics simply breaks down. The pressures here are not just immense, they are almost a logical absurdity, exceeding the force that holds an atomic nucleus together by a factor of 10 or more. The density soars to several times that of an atomic nucleus itself. To put that in human terms, if you could somehow bring a single teaspoon of this material to Earth, it would contain more mass than every single mountain, every ocean, and every person on the planet combined. But what is this matter? What does it become when it is compressed far beyond the state of neutrons? The truth is, we do not know. This is the greatest unsolved puzzle in astrophysics. Theorists propose fantastical possibilities. The intense pressure might be so overwhelming that it shatters the neutrons themselves, breaking them apart into their most fundamental constituents, quarks and gluons. The inner core could become a Quark-Gluon Plasma, a primordial soup of particles that has not existed freely since the first microsecond after the Big Bang. Or perhaps it forms a Hyperon soup, a brew of exotic particles that are normally incredibly unstable and short-lived, but here are stabilized by the sheer pressure. Some of the most exotic theories suggest this material could even become a color superconductor, a substance that conducts electrical current with literally zero resistance, but in a way that operates on the fundamental nuclear force, not electricity. These are not just different states of matter, they are entirely new phases of reality, predicted by mathematics but never observed in any laboratory. Probing this hidden heart is not just about understanding a star, it is about pushing the very limits of the standard model of particle physics, our rulebook for the universe. The behavior of matter in this impossible realm could reveal new fundamental forces or hint at the existence of particles we have not yet dreamed of. The inner core is a locked door, and behind it may lie the next revolution in our understanding of the cosmos itself. So how do we peer into that hidden heart and determine which of these exotic possibilities is real? The key lies in a deceptively simple concept called the equation of state. Think of it not as a complex formula, but as the ultimate personality profile for matter under pressure. It describes precisely how matter pushes back when you try to crush it to an impossible density. Does it resist fiercely, or does it yield easily? The answer to that question defines everything about a neutron star. Theorists have proposed many different equations of state, each one a different prediction for how matter behaves when the rules break down. These models fall into two broad categories. A soft equation of state suggests that matter is relatively squishy, offering little resistance to the star's crushing gravity. In this scenario, the star gets compressed into a very small, incredibly dense object. A stiff equation of state, on the other hand, paints a picture of matter that is fiercely resilient, stubbornly fighting back against collapse. This results in a larger, less dense star. This is not just an academic debate. The equation of state directly predicts the maximum possible mass a neutron star can have before it loses its fight against gravity and collapses into a black hole. Some soft equations predict a low maximum, perhaps only 2 times the mass of our Sun. Stiffer models allow for much heavier stars, perhaps even 2.5 solar masses or more. So how do we test these ideas? We go out and find real neutron stars and measure them. Every time we precisely measure the mass and radius of one of these cosmic corpses, we get a critical data point. It is like finding a key and seeing which theoretical lock it fits. The discovery of a neutron star with a mass of 2 solar masses was a landmark event, immediately ruling out many of the softer, more compressible models. These stars were simply too heavy and too large to be explained by matter that was too squishy. Each new measurement, each precise observation from telescopes across the electromagnetic spectrum, brings us closer to identifying the one true equation of state that governs matter in its most extreme form. This is not just about cataloging stars, it is a grand cosmic experiment, using the universe itself as our laboratory to finally answer the question of what lies within. This relentless cosmic investigation hinges on a single, crucial measurement, the precise mass of a neutron star. Without knowing how heavy these objects truly are, the equation of state remains a list of abstract possibilities. To weigh the impossible, astronomers turn to the cosmos's most reliable scales, binary star systems. When a neutron star has a companion, whether it is another neutron star or the dense remnant of a sun-like star called a white dwarf, their orbital dance reveals their deepest secrets. By applying the laws of orbital motion first described by Johannes Kepler and then refined by Einstein's theory of general relativity, scientists can track the subtle wobbles and timing shifts in their orbits. It is like watching two dancers in a perfectly choreographed routine, where the slightest misstep reveals the weight of each partner. The most precise measurements come from double neutron star systems, where the intense gravitational fields create tiny, predictable ripples in spacetime itself. These ripples allow for mass calculations of breathtaking accuracy. One of the heaviest neutron stars ever found goes by the catalog name PSRJ 0348+0432. It clocks in at almost exactly 2 times the mass of our own Sun, all compressed into that city-sized sphere. This single measurement sent a shockwave through theoretical physics. A 2-solar mass neutron star is a monumental discovery. It acts as a strict gatekeeper for the equation of state, immediately disqualifying any soft or squishy model of matter that would have collapsed under such a tremendous weight. It tells us that the material inside a neutron star must be incredibly stiff and resilient, fiercely resisting the final plunge into a black hole. Every such measurement is a direct test, a real-world experiment that confirms or shatters our theories about the fundamental nature of reality under pressure. Mass alone cannot solve the puzzle of the core. To truly understand the nature of this impossible matter, we need a second measurement, the star's radius. The size of this city-sized object is the other critical piece of data that locks the equation of state into place. Think of it like trying to identify a material by its properties. Knowing only its weight is not enough. You need to know its volume to calculate its density. Is the star a compact, incredibly dense object or a larger, slightly less compressed one? The answer tells us whether the matter inside is soft and yielding or stiff and resilient. But how do you measure the radius of an object 20,000 light-years away? An object so small it would be a mere pinprick of light in even our most powerful telescopes. The answer arrives in the form of X-ray light. Neutron stars are born searingly hot and cool over millennia, glowing fiercely in X-rays. Scientists have developed ingenious techniques to decode this high-energy light. One method involves studying hotspots, areas on the star's magnetic poles heated by infalling gas. As the star spins, these bright spots rotate in and out of view, causing the X-ray brightness to pulse. The precise pattern of these pulses contains hidden information about the star's size and how its immense gravity bends the very path of the light heading toward us. Another method analyzes the light from the entire star's surface as it cools. The spectrum of this X-ray emission, its specific color and intensity, is shaped by the star's gravity and radius. By carefully untangling these signals, astronomers can estimate just how wide this cosmic cannonball truly is. This is the dedicated mission of instruments like NAS, a Neutron Star Interior Composition Explorer, or NICER, an X-ray telescope mounted on the International Space Station. NICER's goal is to measure neutron star radii with an accuracy of just a few percent. That level of precision is transformative. It would allow us to discard entire families of theoretical models, dramatically narrowing the list of possible substances that could exist in the core. A precise radius measurement, combined with a known mass, is the key that will finally unlock the door to the neutron star's hidden heart. But perhaps the most dramatic way to weigh and measure these stars involves no light at all. It relies instead on the stretching and squeezing of space itself. When two neutron stars are locked in a final, fatal dance, they do not spiral inward silently. Their immense masses, whirling around each other hundreds of times per second, churn the very fabric of space-time, sending out ripples known as gravitational waves. These are not waves of light or sound, but literal distortions in the geometry of the universe. For decades, they were only a prediction of Einstein's theory. Then, on August 17, 2017, a new era began. A gravitational wave observatory called LIGO detected a signal, given the name GW170817. It was the unmistakable chirp of two neutron stars circling ever closer until they merged in a cataclysm of unbelievable energy. This single event was a scientific bonanza, observed by telescopes across the globe. But for those probing the inner secrets of neutron stars, the gravitational wave signal held a special clue. In the final moments before the collision, the tidal forces between the two stars became unimaginably strong. Each star's gravity tries to tear the other apart, stretching it into a football shape. How much a star deforms under this pull is called its tidal deformability. This property is a direct tattletale for the equation of state. A star with a soft, squishy interior will be easily distorted, its shape stretching dramatically. A star with a stiff, rigid core will resist, holding its shape almost to the very end. The subtle details encoded in the gravitational waves from GW170817 allowed scientists to measure this tidal deformability for the first time. The data pointed toward stars that were relatively large and resistant to deformation, favoring the stiffer end of the equation of state spectrum. This ruled out the most extremely soft and compressible forms of matter. With one cosmic event, we gained a completely new tool to probe the heart of a neutron star, not by the light it emits, but by the way it warps the universe around it in its final moments. The deadliest beasts in the neutron star menagerie are born from a final, frantic spin. When a massive star collapses, its magnetic field, woven through its plasma like threads in a cosmic tapestry, is compressed and amplified to an almost inconceivable degree. The result is a magnetar, a neutron star whose magnetic field is 1,000 times more ferocious than that of a regular pulsar. To grasp this power, picture a magnetic field so strong it becomes a tangible, destructive force. If you were to approach within 1,000 kilometers of a magnetar, its magnetic field would effortlessly scramble the atomic structure of your body, tearing you apart on a subatomic level long before gravity even had a chance to crush you. This is not a dormant power. It is a volatile, seething energy that constantly strains the star's crystalline crust. The pressure is relentless, and when the crust finally gives way, the resulting starquake is a cataclysm of cosmic proportions. In a single, blinding flash lasting less than a second, a magnetar can unleash more energy than our Sun will radiate over the next 100,000 years. These are the most powerful explosions in the galaxy since the Big Bang itself, titanic bursts of X-rays and gamma rays that can temporarily overwhelm satellites and even affect Earth's upper atmosphere from tens of thousands of light-years away. For physicists, these violent outbursts are not just spectacles, they are priceless experiments. The magnetic fields around a magnetar are so profoundly strong that they warp the fundamental nature of reality. They can polarize the vacuum of space itself, a void we once thought of as nothing. In this twisted environment, the magnetic field forces the empty vacuum to behave like a crystal, bending and even splitting the light that tries to pass through it. Photons, the particles of light, are compelled to merge and transform in ways impossible anywhere else in the universe. A magnetar's fury gives us a fleeting glimpse into a realm where the rules of quantum electrodynamics are pushed to their absolute breaking point, a natural laboratory for the most extreme physics imaginable. This ultimate breakdown of matter begins when pressure crosses a critical, almost unimaginable threshold. Deep within the neutron star's heart, the neutrons themselves can no longer hold their identity. They are not fundamental particles, but are each made of three smaller particles called quarks, held together by the nuclear glue known as gluons. Under normal conditions, the force binding them is so powerful that no quark can ever be observed alone. It is a law of the universe, a form of permanent confinement. But here, in the core of a neutron star, that fundamental law is broken. The pressure becomes so overwhelming that it overwhelms the force of confinement itself. The neutrons shatter. They dissolve into a seething, chaotic soup of their constituent parts, a state known as a Quark-Gluon Plasma. This is not a gentle melting, but a violent deconstruction of reality's building blocks. For a fleeting moment, this was the state of the entire universe, just microseconds after the Big Bang. A neutron star's core is the only place in the modern cosmos where we believe this primordial fire might still be burning. Yet even this chaotic soup might not be the final state. As the pressure mounts further, the frenetic quarks could suddenly snap into an orderly, crystalline arrangement. This is the theoretical color superconductor, a material that would carry currents with perfect efficiency, not of electricity, but of the strong nuclear force itself. The name comes from the property of quarks known as color charge, which has nothing to do with visual color, but is the source of their immense binding power. In this state, pairs of quarks could flow without any resistance whatsoever, a perfect quantum fluid locked within the star's center. This leads to one of the most profound questions in modern astrophysics. Could an entire star be made of this stuff? Is a quark star possible, an object even denser and more exotic than a neutron star? Or do we live with hybrid stars, objects with a familiar neutron-rich outer core shielding a secret heart of pure, unconfined quark matter? The answer lies at the very frontier of science, a place where the physics of the colossal, gravity-dominated cosmos collides directly with the physics of the impossibly small. The very identity of matter may dissolve in the star's deepest core. Another tantalizing possibility is that neutrons do not simply break into quarks, but instead transform into something far more exotic. They could become hyperons. You can think of a hyperon as a neutron's strange and unstable cousin. Like protons and neutrons, hyperons belong to the baryon family, the heavy particles that make up the nuclei of atoms. But a hyperon carries a secret ingredient, at least one strange quark. the ordinary up and down quarks that build our familiar world are replaced in part by this strange quark, a fundamental particle that is heavier and far more ephemeral. In the relatively tame environment of Earth, Hyperons are fleeting ghosts decaying into other particles in a fraction of a nanosecond. But inside a neutron star's core, the rules change completely. The pressure is so phenomenally high that it actually becomes energetically favorable, even efficient, for some of the densely packed neutrons to convert themselves into these strange particles. The core could become a Hyperon soup, a bizarre broth of matter that is fundamentally alien to everything we know. This strange matter, however, presents a serious theoretical dilemma. Hyperons interact with each other differently than neutrons do. Their presence generally makes the overall core material softer, more compressible. It is as if you replaced the sturdy bricks in a building's foundation with a dense, but ultimately more yielding, rubber. This softening of the equation of state makes it harder for the star to push back against its own immense gravity. According to many straightforward models, a Hyperon-rich core should not be able to support the massive two-solar, mass neutron stars we have definitively observed in the cosmos. The star should have collapsed into a black hole long before it reached such a weight. This glaring contradiction is known as the Hyperon Puzzle, and it is one of the most compelling problems in theoretical physics today. Its existence forces physicists to invent new solutions, to propose that at these incredible densities, previously unknown forces must emerge. Perhaps Hyperons interact with such tremendous repulsion that they stiffen the core despite their strange nature. The puzzle is not a dead end, but a guiding star pointing toward new physics that can only be found in the heart of a collapsing star. Deep within the neutron superfluid, another cosmic dance is unfolding. Scattered among the vast sea of neutrons is a small population of protons, perhaps only one for every 20 neutrons, yet these protons hold a power far beyond their numbers. While the neutrons have become a frictionless superfluid, the protons are likely undergoing their own transformation, becoming a superconductor. In this state, electricity flows without any resistance whatsoever. There is no heat, no loss of energy. A current once started in this proton sea would circulate forever, locked within the star's heart. This isn't just a curious detail, it is the probable engine for the star's immense magnetic field. The combination of this perfectly conducting proton fluid and the star's insane rotation creates a natural dynamo. Picture a colossal, spinning sphere of superconducting wire, generating electrical currents of astronomical magnitude. These currents, in turn, produce the magnetic fields that define the star's most dramatic interactions with the cosmos. But this perfect system is not entirely stable. The superconducting protons and the superfluid neutrons must coexist, and their relationship is a turbulent one. The magnetic field, which is woven through the proton superconductor, cannot exist as a smooth, continuous force. Instead, the physics demands that the field be organized into incredibly thin, whirlpool-like tubes of magnetic flux, each one carrying a precisely defined or quantized amount of magnetic energy. These microscopic cosmic tornadoes are forced to thread their way through the churning neutron sea. The frictionless neutrons simply flow around these magnetic vortices, often pinning them in place. But during a starquake or a sudden spin-up, this delicate balance can be shattered. When the vortices suddenly unpin and surge outward through the superfluid, they drag the star's internal magnetic field with them. This gradual migration of magnetic flux from the interior to the crust and beyond may be the key to understanding why pulsars slowly, over millions of years, lose their magnetic fury. The steady, metronomic pulse we detect from a distant pulsar is therefore the surface manifestation of a deep and complex relationship. a perpetual negotiation between a frictionless fluid and a perfect conductor, forever spinning in the dark. The silent, fading warmth of a neutron star tells a story more revealing than its most violent pulses. These stellar embers are born in the fiery chaos of a supernova, hotter than the core of any ordinary star, with temperatures soaring into the billions of degrees. But they do not stay that way. They are cosmic corpses cooling relentlessly in the frigid vacuum of space, and the precise rate of that cooling is a direct window into their deepest, most hidden physics. It is like trying to understand the inner workings of a sealed engine by simply placing a hand on its casing and feeling how quickly the heat dissipates. The key to this rapid cooling lies in ghostly messengers, neutrinos. These nearly massless particles barely interact with normal matter, allowing them to escape directly from the star's core, carrying vast amounts of energy with them into the void. The most efficient engine for this process is known as the direct Urca process. It is a subatomic cycle where a neutron decays into a proton and an electron, emitting a neutrino in the process, only for the proton and electron to immediately recombine back into a neutron, releasing another neutrino. This continuous cycle acts like a radiator at the heart of the star, bleeding heat away at a phenomenal rate. But there is a catch. For the direct Urca process to operate, the density of particles must reach an extremely high threshold. In many neutron star models, this threshold is not met, and a slower, less efficient cooling process dominates. This is where observation becomes our guide. By measuring the surface temperatures of neutron stars of various, well-estimated ages, astronomers can construct a cooling curve, a timeline of their thermal death. When a star's observed temperature is significantly cooler than a standard model predicts, it is a powerful clue. It suggests that something inside is enhancing the neutrino emission, acting as a super-efficient coolant. This deviation points directly to the presence of exotic matter. Theorists propose that particles like pions or kaons, which are normally unstable and short-lived, could be stabilized by the immense pressure. If these particles exist in the core, they would open new channels for neutrino emission, accelerating the star's cooling far beyond what ordinary neutrons alone could achieve. Each precise temperature measurement from an aging neutron star is therefore a vote for or against a specific reality inside that core. A star that remains too warm for its age tells us its interior is likely dominated by standard, slow cooling matter. But a star that has chilled with unexpected speed is signaling the presence of the extraordinary, a core brimming with exotic particles that are rewriting the rules of thermal decay. By reading this cosmic cooling curve, we are not just watching a star grow cold. We are decoding the very ingredients of matter squeezed into oblivion. That steady, metronomic pulse from a distant pulsar is a cosmic lie of perfect regularity. Its true nature is betrayed by sudden, tiny jumps in rhythm known as glitches. For decades, these events were mere curiosities, unexplained hiccups in the data. Today, we understand they are not malfunctions but messages. Each glitch is a direct telegram from the quantum storm raging inside the star, a fleeting window into the superfluid heart of the beast. The mechanism is a masterpiece of cosmic engineering. Picture the star's rigid crust spinning at a steady rate, slowly losing energy to its own radiation and gradually slowing down over millennia. But beneath this solid shell, the neutron superfluid is a different universe. It is a frictionless quantum liquid, and once it begins to spin, it wants to spin forever. The two components are linked by a forest of microscopic tornadoes called vortices. In the superfluid, rotation is quantized, meaning it can only spin at specific, discrete rates. These vortices are the physical manifestation of that spin. Normally, these tiny whirlpools are pinned or locked into place by the atomic lattice of the solid crust above them. This pinning is what allows the superfluid to spin at a different, slightly faster rate than the crust. It is a system under immense strain, like a powerful motor held back by its brakes. Then the Starquake happens, a shift in the crystalline crust, perhaps triggered by the build-up of stress from the slowing spin, suddenly shakes the entire structure. This tremor is enough to release the brakes. In an instant, vast numbers of these pinned vortices break free. They surge outward from the star's rotation axis, like a school of fish suddenly changing direction. This mass exodus carries with it a tremendous amount of angular momentum, the same property that makes a spinning ice skater speed up when they pull their arms in. This pent-up rotational energy is dumped directly into the solid crust. The entire star, a body with the mass of a sun compressed into a city, experiences a sudden, measurable jolt. Its rotation speeds up by a tiny fraction in a fraction of a second. Our telescopes on Earth register this as a glitch, a permanent step-like increase in the pulsar's spin rate. The details of this event are a treasure trove of information. The size of the glitch tells us how much superfluid was suddenly coupled to the crust. The time it takes to recover as the system finds a new equilibrium reveals the nature of the friction, or the lack thereof, between the superfluid and the rest of the star. The frequency of glitches hints at the strength of the pinning forces deep within the crust. By listening to these rhythmic anomalies, we are essentially performing stellar seismology. We are mapping the interior of an object we can never see, using the vibrations that ripple through its structure. Each glitch is a unique experiment, allowing us to test our theories of quantum fluids under the most extreme conditions imaginable. The very fabric of reality warps around these cosmic cinders. Neutron stars are so unimaginably dense that their gravity does not merely pull on objects, it twists the stage upon which the universe plays out. This is the domain of Einstein's general relativity, where gravity is the curvature of spacetime itself. Around a neutron star, this curvature is not a subtle effect. It is a profound distortion, a deep well in the cosmos that bends the paths of light and stretches the flow of time. If you could place a clock on the surface of a neutron star, its relentless ticking would slow to a crawl compared to a clock far out in space. This is not a mechanical failure. It is time itself, stretched and dilated by the immense gravitational field. An astronaut hovering near the star would age far more slowly than their colleagues on a distant ship, a dramatic demonstration of a theory that often feels abstract and distant. This warping of spacetime creates the most stringent tests for Einstein's ideas. The perfect arena for these experiments is a binary system where two neutron stars orbit one another. As they whirl through their fatal dance, they are not moving through a static, flat space. They are tracing paths along the curves and contours their own masses create. This leads to a subtle, yet measurable, effect called the precession of the orbit. The point of closest approach, the periastron, does not stay fixed. It slowly rotates around the system, tracing a rosette pattern in space. This is precisely what general relativity predicts, and observations of these systems have matched the theory with breathtaking precision. The most famous of these, the Hulse-Taylor binary pulsar, provided the first indirect evidence for gravitational waves and earned its discoverers a Nobel Prize, offering some of the strongest confirmation that Einstein was right. But the ultimate tests are still to come. When two neutron stars spiral inward and finally merge, they do not just emit a final chirp of gravitational waves. The entire in-spiral process is a rich song encoded with information about how spacetime behaves under the most extreme stress imaginable. By meticulously analyzing the gravitational wave signal, scientists can probe the strong field regime of gravity, a realm where the predictions of general relativity could begin to fray at the edges. Does matter respond to gravity exactly as the theory dictates when densities approach that of an atomic nucleus, or will we find tiny, telling deviations? Any inconsistency, no matter how small, would be a scientific earthquake. It could be the first clue leading to a new, more complete theory of gravity, one that might finally reconcile the cosmic scale of relativity with the quantum world. Each neutron-star merger we detect is not just the death of two stars. It is a direct interrogation of the fundamental laws governing our universe, pushing our understanding to the absolute limit. This delicate balance is a cosmic tightrope stretched over an abyss. A neutron star exists only within a razor-thin sliver of possibility, a precise equilibrium between two ultimate forces. On one side is the relentless inward crush of gravity, a force that wants nothing more than to compress the star into a singularity. Pushing back is the outward pressure generated by the degenerate neutrons and other exotic particles, a quantum mechanical rebellion against being forced into the same state. This fundamental standoff carves out a very narrow range of permissible masses and radii for these objects. It is a strict cosmic zoning law. If a newborn stellar core is too light, perhaps less than about 1.5 times the mass of our Sun, the collapse will simply not be violent enough to crush atoms into neutrons. It will stop at a white dwarf, a dense but far less extreme object. But if the core is too heavy, the quantum pressure of the neutrons will prove insufficient. The star will lose its fight, its resistance will crumble, and gravity will achieve total victory, crushing the star past the point of no return into a black hole. The precise value of this maximum mass is one of the most sought-after numbers in all of astrophysics. It is not just a statistic, it is a direct measurement of the ultimate strength of matter itself. Finding this upper limit tells us, in no uncertain terms, exactly how stiff matter can become when pressed to its absolute breaking point. Every time astronomers confirm the existence of a new, exceptionally heavy neutron star, like the two solar mass pulsars we have found, it sends theorists back to their chalkboards. These colossal objects push the theoretical limit upward, challenging our models to explain what physical mechanism could possibly provide such immense internal pressure. How can matter be so fiercely resilient that it can support a mass twice that of our Sun in such a tiny volume, yet still resist the final, all-consuming pull of a black hole? The answer is locked within the equation of state, and each new heavyweight champion we discover forces us to consider more exotic possibilities, from quark matter to hyperons with powerful repulsive forces, to keep this cosmic tightrope walker from falling. Even the rigid crust cannot escape the quantum chaos below. As you descend from that crystalline surface toward the churning superfluid ocean, you enter a twilight zone where matter undergoes its most bizarre transformation. Physicists call this region the inner crust, and the material that forms here has earned a whimsical yet deadly serious name: nuclear pasta. Here, the gravitational pressure is so immense that the familiar atomic nuclei, already crammed shoulder to shoulder, can no longer maintain their spherical shapes. They are flattened, stretched, and squeezed into long, thin tubes that physicists call nuclear spaghetti. Increase the pressure just a bit more, and these tubes themselves merge into flat sheets, a phase known as nuclear lasagna. Go deeper still, and the sheets are punctured with holes, creating a structure resembling a waffle. In the final descent toward the core, these waffle-like sheets collapse into dense, spherical clusters once more, but now they are suspended within the neutron sea, like nuclei in a cosmic soup. This entire menagerie of shapes, all born from the struggle between the nuclear force and gravity, forms the nuclear pasta. This material is not just strange, it is unimaginably strong. Its sheer modulus, a measure of rigidity, is calculated to be billions of times greater than that of high-grade steel. A single cubic centimeter of nuclear pasta would require the force of 100 billion tons to break. This makes it, by a colossal margin, the strongest known material in the entire universe. Its existence solves some of the great mysteries of neutron stars. The incredible strength of this pasta layer is what allows the solid crust to lock or pin, the vortices of the superfluid spinning beneath it. This pinning is the very mechanism that builds up the rotational energy released in a starquake or a spin glitch. The rigidity of the nuclear lasagna sheets and spaghetti strands directly controls how the star's crust cracks and how its magnetic field slowly migrates outward over millions of years. Every glitch we detect is in part a story written by the breaking and reforming of this impossibly strong material. To study nuclear pasta is to explore the ultimate frontier of materials science, where the principles that govern the strength of steel and diamond are replaced by the pure mathematics of the strong nuclear force. It is a realm where the fate of a star and the signals it sends across the galaxy are dictated by the behavior of matter shaped like a cosmic dinner. Deep within this churning quantum sea, even the electrons are not safe. As the density climbs to staggering heights, the energy of these trapped particles, their Fermi energy, soars. This creates a pressure cooker so intense that a strange and fundamental swap becomes possible. It suddenly takes less energy to create a new, heavier particle than to keep packing in more high-energy electrons. This is the moment the muon enters the story. Think of a muon as the electron's bulkier, more unstable sibling. It carries the same negative charge, but it is over 200 times heavier. In our tame world, muons are fleeting cosmic visitors, produced in particle accelerators or by cosmic rays, decaying into electrons in mere microseconds. But inside a neutron star, the rules of survival are rewritten. The crushing pressure stabilizes them, and they become a permanent, vital component of the soup. Their arrival triggers a cascade of subtle changes that reshape the star's interior. To maintain an overall neutral charge, the presence of negatively charged muons forces a slight reshuffling, requiring a few more protons to balance the books. This changes the delicate particle cocktail, opening up new and efficient pathways for the star to cool. Neutrinos, those ghostly particles that carry energy away, can now be produced through reactions involving muons, acting as a new radiator deep within the engine. This muon-driven cooling can cause the star to lose its ferocious heat more rapidly than we might otherwise predict. Furthermore, the very presence of these heavy particles subtly softens the star's resistance to gravity. While neutrons provide a stiff, resilient pressure, muons introduce a slightly more compressible element into the mix. Imagine a building where you replace a few of the solid steel beams with a denser, but marginally more flexible alloy. The building still stands, but its maximum possible height is slightly reduced. In the same way, a muon-rich core predicts a neutron star that is a little more compact for a given mass, slightly lowering the theoretical maximum mass these objects can achieve before collapsing into a black hole. This is the profound lesson of the muon. It is not an exotic, theoretical phantom, but a well-known particle from our own laboratories. Yet when placed into the heart of a neutron star, it behaves in entirely unexpected ways, becoming a key player in the thermal and structural fate of the entire object. It proves that to understand the most extreme states of matter, we must be prepared for even the familiar to become strange. The ultimate secret of the core might not be a new state of matter, but an entirely new particle. Our current rulebook for particle physics, the Standard Model, may be incomplete, and the neutron star's heart is the perfect laboratory to find what is missing. One of the most promising candidates is a ghostly particle called the action. This hypothetical entity was first dreamed up to solve a deep puzzle in the strong nuclear force, a question of why neutrons do not interact with electric fields in a way they theoretically should. The mathematics demanded a fix, and the action was the elegant solution. It is predicted to be incredibly light and barely interactive, a cosmic will-o'-the-wisp. But in the furnace of a neutron star's core, these shy particles could be produced in staggering numbers. The intense magnetic fields and searing temperatures would act like a factory, forging actions that then stream unimpeded out of the star, carrying precious thermal energy with them. This would be a new, invisible cooling channel. If actions are real, they could explain why some neutron stars appear to be cooling faster than our models predict, their heat vanishing into the void on the backs of these unseen particles. This makes every unexpectedly cold neutron star a potential signpost, pointing toward a fundamental new piece of reality. But actions are not the only possibility. The immense gravity of a neutron star could act as a trap for another great cosmic mystery, dark matter. Over billions of years, these elusive particles, which we know must exist from their gravitational effects on galaxies, could be drawn into the star's core. They would accumulate, a growing shadowy mass at the star's center. If certain types of dark matter particles can annihilate with one another, this process would inject a new and unexpected source of heat into the core, slowing the star's cooling process to a crawl. A neutron star that remains mysteriously warm for its advanced age could be a beacon, signaling that it has captured a dark heart. This transforms these distant objects from mere cosmic curiosities into the most sensitive particle detectors in the universe. They operate on scales and at energy levels far beyond the reach of any machine we could ever build on Earth. By carefully reading the thermal death of these stars, by measuring their cooling curves and hunting for anomalies, we are not just studying stellar corpses. We are conducting a grand search for the invisible components of the cosmos, using the universe's most extreme environments to probe for shadows. A fundamental property of any substance is the speed of sound, the rate at which a pressure wave can travel through it. In a neutron star, this is not a single, simple number. It is a journey. As you descend from the brittle crust into the churning quantum oceans and finally toward the mysterious inner core, the speed of sound changes dramatically. It is a direct measure of the material's stiffness, of how fiercely it pushes back when compressed. In the outer layers, sound travels at a significant fraction of light speed. But in the deepest core, where matter may have dissolved into a Quark-Gluon Plasma or a color superconductor, theories suggest the speed of sound might approach its ultimate limit, the speed of light itself. This is not just a curious detail, it is a fundamental rule of the universe, causality, the principle that no information, no signal, no influence can travel faster than light, sets a hard ceiling. The speed of sound within the star cannot exceed this cosmic speed limit. This simple, profound fact becomes one of the most powerful tools we have to rule out theories. Any proposed equation of state that predicts a sound speed faster than light in the core must be wrong. It violates the most basic tenet of physics. So, by studying how the sound speed must change with the incredible density inside a neutron star, we can draw a map of possible realities. A sound speed that rises and then levels off points toward one family of exotic matter. A sound speed that climbs steeply and peaks hints at another. This invisible, fundamental wave guides us, constraining the zoo of theoretical possibilities and bringing us closer to understanding what truly happens to matter when it is pressed into oblivion. The true power of modern astrophysics lies not in a single telescope, but in a chorus of voices. This is the essence of multi-messenger astronomy, a coordinated effort to observe the universe using every possible signal at our disposal. The event that truly ushered in this new era was the neutron star merger known as GW170817. Its story was not told by one instrument, but by many. The first alert was the faint ripple in spacetime, the gravitational wave chirp detected by LIGO. Seconds later, orbiting satellites caught a brief, intense flash of gamma rays. Then, telescopes across the globe and in space swiveled to that patch of sky, capturing the event in X-rays, ultraviolet, visible light, and radio waves. They witnessed a hot, expanding cloud of material glowing with the radioactive decay of newly forged elements. This single, coordinated observation solved a cosmic mystery that had persisted for decades. The data provided undeniable proof that the violent collisions of neutron stars are cosmic forges, the primary source of the universe's heaviest elements, including vast quantities of gold and platinum. Every ounce of gold in a wedding ring or a microprocessor was likely born in such a cataclysm, spewed out into the galaxy to one day become part of our world. Beyond this profound discovery, the combined data from all these messengers placed the tightest constraints yet on the neutron star equation of state. The way the stars deformed each other before merging, the brightness and duration of the resulting glow, all of it had to be consistent with a single model of matter's behavior. This multifaceted view immediately ruled out many theoretical possibilities, telling us that the material inside must be relatively stiff and resilient. This collaborative approach is the future. By combining the space-time shudders from gravitational wave observatories with the high-energy snapshots from X-ray telescopes, the steady pulses from radio dishes, and even the potential future detection of neutrinos, we are building a complete, three-dimensional picture of these impossible objects. We are no longer just listening to a single note, but hearing the entire symphony of a neutron star's life and death, and in doing so, finally deciphering the secrets of matter under pressure. That delicate balance between crushing gravity and quantum pressure is not just a cosmic accident. It is governed by a profound and elegant physical law, one that dictates the very structure of stars and galaxies. The Virial Theorem is a cornerstone of astrophysics, a mathematical rule that describes how self-gravitating systems like neutron stars achieve stability. In its simplest form, it states that for a system in equilibrium, the total internal kinetic energy must be balanced against half of its gravitational potential energy. But what does that mean for our city-sized cinder of a star? The kinetic energy here is not the heat of a fire, but the raw quantum mechanical motion of the degenerate neutrons and other particles. This is their Fermi energy, the relentless pressure that comes from being packed so tightly together that they simply cannot occupy the same quantum state. They are constantly jostling, pushing outward with immense force. This kinetic energy is locked in a perpetual tug of war with the gravitational binding energy, the profound well of potential energy created by the star's own mass pulling everything inward. The Virial Theorem is the rulebook for this standoff. It tells us that these two titanic energies are not independent. They are inextricably linked in a precise ratio. This relationship reveals why a neutron star's mass and radius are not arbitrary numbers. They are a direct consequence of this fundamental balance. For every possible type of internal matter, defined by its unique equation of state, The Virial Theorem dictates a specific family of stable configurations, a narrow range of masses and radii that can exist without immediately collapsing or flying apart. This is why we cannot have a neutron star the size of a planet, or one with 10 times the mass of the Sun. The numbers simply would not add up. The theorem also illuminates the ultimate fate of these objects. As you try to add more and more mass to a neutron star, the gravitational binding energy grows much faster than the internal kinetic energy can possibly keep up with. There comes a point of no return, a maximum mass where the balance prescribed by the Virial Theorem can no longer be satisfied. The quantum pressure of the neutrons is finally overwhelmed. At that critical threshold, the star's resistance crumbles and gravity wins its final victory, forging a black hole. Every precise measurement of a neutron star's mass and radius is therefore a test of this grand universal principle, a confirmation that even in the most extreme corners of the cosmos, matter is bound by the same elegant rules. Gravity may rule the neutron star, but it does not rule alone. There is a second force constantly pushing back, a rebellion born from the star's own furious spin. This is centrifugal force, the same effect that tries to fling you from a merry-go-round. On a neutron star, this outward push directly counteracts the inward crush of gravity, warping the entire object. The result is not a perfect sphere, but an oblate spheroid, a shape slightly squashed at the poles and bulging at its equator. For most neutron stars, this bulge is minuscule, perhaps only a few millimeters high. But for the fastest of them all, the millisecond pulsars, the deformation can be profound. Their equatorial regions can be dozens of meters farther from the center than their poles, a significant distortion for an object only 20 kilometers across. This relentless spin does more than just reshape the surface. It reaches deep into the star's quantum heart, stirring the superfluid ocean and influencing the tangled configuration of its magnetic field. The very spin of a neutron star is a fossil, a permanent record of its violent birth and subsequent life. A leisurely rotator spinning only a few times per minute likely had a quiet formation, collapsing without much drama. But a millisecond pulsar whirling hundreds of times per second tells a very different story. It is a stellar vampire, spun up to impossible speeds by siphoning matter from a companion star. As this stolen gas spiraled inward, it transferred its immense angular momentum to the dead star, accelerating it into a celestial frenzy. This rotation is not just a detail. It is a fundamental part of the star's identity, a force that sculpts its form and dictates its internal rhythms from the crust all the way down to the mysterious core. The fate of a dying star hinges on a single critical number. Decades before the first pulsar was discovered, a young physicist named Subramanian Chandrasekhar contemplated the ultimate end for stars like our Sun. During a long sea voyage, he performed calculations that would forever change astrophysics. He realized that a star's corpse, a white dwarf, could not exist at any mass. It was supported against gravity by a quantum pressure from its electrons, a force that arises when particles are packed too closely together. But Chandrasekhar showed this electron degeneracy pressure has a strict ceiling. He calculated that if the stellar core remnant exceeds about 1.4 times the mass of our Sun, this quantum pressure abruptly fails. This is the Chandrasekhar limit, the dividing line between a quiet white dwarf and a far more violent demise. For any core more massive than this, gravity wins completely. The electrons are crushed into the protons and the core implodes, either birthing a neutron star or, if even heavier, collapsing directly into a black hole. This foundational discovery revealed that the universe operates with strict mass limits, like cosmic safety regulations for stellar corpses. but the story does not end there. For neutron stars, there is an analogous boundary, the Tolman-Oppenheimer-Volkoff limit. This is the ultimate maximum mass that neutron degeneracy pressure and the strong nuclear force can possibly support. Unlike the precise Chandrasekhar limit, however, this number is shrouded in mystery. Its value depends entirely on the unknown equation of state, the true nature of matter in the core. Is the maximum mass 2.2 solar masses, or 2.5, or perhaps even higher? Each time we discover a heavier neutron star, like the 2 solar mass pulsars, we push this theoretical boundary further out. The quest to find this final number is a direct continuation of Chandrasekhar's pioneering work, a century-long investigation into the absolute strength of matter. Finding the Tolman-Oppenheimer-Volkoff limit would not just tell us how heavy a neutron star can be. It would finally reveal what happens when matter is pressed to the very brink of existence, at the final moment before it vanishes from our universe entirely. These stellar corpses are the universe's ultimate alchemists. While they represent the final state for massive stars, they are also the violent birthplaces of the very atoms that make up our world. The creation of these heavy elements hinges on a frantic race against time known as the rapid neutron capture process, or the R process for short. This is how nature forges about half of all elements heavier than iron, from the silver in jewelry to the uranium that powers nuclear reactors. The recipe is simple in concept but requires a nearly impossible kitchen. You need a raging flood of free neutrons, an atomic deluge so dense that atomic nuclei are bombarded before they have a chance to stabilize. In this frantic environment, a seed nucleus, perhaps a speck of iron, is assaulted. Neutrons slam into it one after another, rapidly building its mass in a blink of an eye. This creates an extremely heavy, unstable isotope. This bloated nucleus cannot last. It immediately undergoes radioactive decay, transforming some of its neutrons into protons. This changes its very identity, moving it to a new spot on the periodic table. Then, the neutron bombardment begins again. This cycle of rapid capture and subsequent decay hops up the ladder of elements, creating gold, platinum, and neodymium in a cosmic instant. For decades, astronomers theorized about where this perfect storm could occur. The answer arrived from the most violent events in the galaxy. When two neutron stars spiral together and merge, they rip each other apart. The collision flings vast clouds of neutron-rich material into space at incredible speeds. This ejected material is the perfect R process crucible, a fog of shattered neutrons and nuclei where element creation can run wild. Similarly, the colossal magnetic eruptions from magnetars could potentially fire jets of neutron-rich matter into their surroundings, seeding space with the ingredients for planets and life. The proof came in a single historic event. The gravitational wave signal of a neutron star merger was followed just seconds later by the detection of a short gamma-ray burst. Then telescopes around the world saw it, a new glow in that patch of sky. This was the kilonova, a transient blaze of light powered entirely by the radioactive decay of freshly minted R process elements. The specific colors and the fading pattern of that light were the unmistakable signature of heavy elements like gold and platinum being forged in real time. That single cosmic collision likely produced an amount of gold weighing more than our entire planet. Every precious metal on Earth, every heavy element in your body, carries the echo of such a cataclysm. We are literally made from the ashes of these dead stars, forged in their final, spectacular deaths. This surface is a battlefield where the vacuum of space confronts solid matter at its absolute limit. A neutron star's gravitational pull is so immense that it fundamentally alters the light struggling to escape. photons climbing away from the surface must spend a tremendous amount of their energy fighting the star's gravity. This saps their strength, stretching their wavelengths and shifting their color toward the red end of the spectrum. This effect, called gravitational redshift, is not a small curiosity. For a typical neutron star, a spectral line that should be blue could appear to us as a deep, dramatic red, a clear signal of the warped spacetime from which it came. This energy loss is a direct signature of the star's compactness, a clue written in the very light we detect, but the surface is far from inert. In binary systems, the star acts as a cosmic vampire, using its gravity to strip gas from a companion. This stolen material, mostly hydrogen and helium, flows onto the surface, piling up into an ever-thickening layer. Under the growing weight and heat, this accreted ocean eventually reaches a flashpoint. The hydrogen fuses into helium in a runaway thermonuclear explosion that engulfs the entire star in a fireball. We see this from Earth as a sudden, brilliant X-ray burst, a flare that can outshine 100,000 suns for a few precious seconds. These X-ray bursts are far more than just cosmic fireworks. They are our most powerful flashlights, momentarily illuminating the star's surface and its immediate environment. The way the burst brightens and then fades, its spectrum and the subtle flickers within it all encode vital information. By analyzing this X-ray light, scientists can perform a kind of cosmic tomography, measuring both the star's mass and its radius with remarkable precision. Each burst is a natural experiment, revealing the physical conditions at this impossible interface where plasma physics, nuclear reactions, and the profound distortions of general relativity all collide. It is here, at this chaotic boundary, that we gather the raw data to test our grandest theories about the heart of the impossible matter within. The silent ticking of pulsars is about to become a chorus. A new generation of observatories is poised to transform these solitary beacons into a vast, interconnected network, revealing secrets they have held for eons. The Square Kilometer Array, or SCAR, is not just another radio telescope. It is a monumental leap, a project spanning 2 continents, designed to listen to the universe with unprecedented sensitivity. When it turns its gaze to the Milky Way, it will not find a handful of pulsars. It will discover tens of thousands of them. Each one is a precision timepiece, and together they form a cosmic GPS system of unimaginable scale. By monitoring the subtle, synchronized deviations in the pulses from this vast array, scientists hope to detect the background hum of low-frequency gravitational waves, the remnant echoes of supermassive black hole mergers from the dawn of time. This is like listening to the deepest notes of the universe's symphony, vibrations too slow and vast for any other instrument to hear, but the revolution does not stop with radio waves. On the other side of the spectrum, gravitational wave detectors like advanced LIGO and Virgo are being constantly refined. Their next observing runs will capture the final moments of colliding neutron stars with breathtaking clarity, revealing not just the fact of their merger, but the intricate details of how they tear each other apart. Each chirp from these cosmic collisions is a direct probe of the star's internal structure, encoded in the way space-time itself ripples. To complete the picture, a new fleet of X-ray eyes is heading to space. Observatories like Athena and XRISM are designed for high-resolution spectroscopy. They will not just see the hotspots on a neutron star's surface, they will analyze the precise chemical fingerprint of the X-ray light emitted from these furnaces. This is like moving from a blurry photograph to a detailed forensic analysis. They will measure the gravitational redshift with such precision that we can finally pin down the star's mass and radius simultaneously, a critical step toward locking in the true equation of state. These separate streams of data, from radio pulses to space-time ripples to X-ray spectra, are no longer isolated clues. They are converging into a single, powerful current. For the first time, we will be able to combine them, creating a detailed tomographic map of a neutron star's interior. We will see the thickness of the crust, the dynamics of the superfluid ocean, and the properties of the mysterious core. This multi-messenger approach is the key that will finally unlock the central mystery, telling us definitively whether the heart of a neutron star is a quark soup, a Hyperon brew, or something even more fantastical. The coming decade will not just add to our knowledge, it will rewrite the textbook on the fundamental nature of matter itself. These stellar corpses rarely drift through the cosmos alone. Many are found locked in a gravitational embrace with another star, and this partnership transforms them into unparalleled cosmic laboratories. The dance begins with gravity's relentless pull. A neutron star can act as a celestial vampire, siphoning gas from its companion. This stolen material does not fall directly onto the surface. Instead, it spirals inward, forming a flat, swirling vortex of superheated plasma known as an accretion disk. This disk glows with a ferocious intensity, emitting powerful X-rays that we can detect across the galaxy. But the transfer of matter is also a transfer of energy. As this gas spirals down onto the neutron star, it carries immense angular momentum, effectively giving the dead star a spin. This is the secret behind the fastest pulsars in the universe, the millisecond pulsars. An old, slow-spinning neutron star can be recycled, spun up to a frenzy of hundreds of rotations per second by this steady diet of stellar gas. The gravitational forces at play in these systems are so extreme that they can do more than just pull gas. In some tight binaries, the neutron star's gravity is powerful enough to tidally disrupt its companion, stretching the entire star into a teardrop shape and slowly tearing it apart over time. These violent interactions are not just a spectacle, they are our most precise scales. By observing the orbital wobbles and timing shifts in these binary dances, astronomers can measure the neutron star's mass with breathtaking accuracy. Every flicker in the X-ray emission, every subtle change in the pulse timing, is a data point that helps us rule out theories about what lies within. And these systems hold an even grander secret. They are the progenitors of the most violent events in the universe. Two neutron stars in a binary system will slowly lose orbital energy by emitting gravitational waves, their paths tightening over billions of years until they finally collide in a cataclysm that shakes the fabric of space-time and forges the universe's heavy elements. Every binary neutron star we study is a preview of a future merger, a ticking clock counting down to a cosmic explosion that will one day illuminate the darkness with the birth of gold. The heart of a neutron star defies any single branch of science. To even attempt a model of its interior demands a merger of physics itself, a seamless fusion of nuclear physics, particle physics, Einstein's general relativity, and the complex dynamics of magnetized fluids known as magnetohydrodynamics. Each of these disciplines provides a vital piece of the puzzle, yet none can see the full picture alone. The fundamental obstacle is one of scale. The densities and energies found deep within a neutron star are so phenomenally extreme that they exist in a realm far beyond the reach of any particle accelerator or laboratory experiment on Earth. Our most powerful machines can only hint at the conditions present there. This forces physicists into a delicate and uncertain dance of theoretical extrapolation, stretching our known laws to their absolute breaking point and hoping they do not snap. How do you predict the behavior of matter in a place you can never visit? You build your best possible mathematical bridges from the known to the unknown. Lattice quantum chromodynamics performs calculations on a discrete grid to probe the strong force that binds quarks. Chiral effective field theory offers a framework for describing the interactions between neutrons and protons at lower densities. Phenomenological models use simpler, adjustable parameters to approximate the incredibly complex nuclear interactions. Each approach offers a valid but incomplete perspective, like different maps of the same uncharted continent. The ultimate test is whether these theoretical landscapes can align with the hard, cold data from the cosmos itself. This is where supercomputers become our virtual laboratories. They run monumental simulations of colliding neutron stars and the final moments of stellar collapse, weaving together all these disparate threads of physics into a dynamic, digital reality. These simulations are not just animations, they are rigorous experiments in a virtual universe, testing whether our combined theories can produce the masses, the radii, the gravitational wave signals, and the explosive kilonovae that our telescopes actually observe. Every glitch in a pulsar's timing, every precise mass measurement, and every ripple in spacetime from a merger acts as a judge, ruling entire families of models in or out of contention. This grand effort to model the unmodelable is more than an academic exercise. It is a profound stress test for our entire understanding of the fundamental forces of nature, pushing our knowledge to the very edge of existence to see what, if anything, holds true. That lingering question of why this matters, why we should peer into these distant, impossible objects, finds its answer closer to home than you might think. Look at your own hand. The iron in your blood that carries life-giving oxygen was born in the heart of a long-dead star. But what about the iodine essential for your thyroid or the gold in a wedding ring? These heavier elements require a more violent birth. They are forged in the cataclysmic mergers of neutron stars. Every time two of these stellar corpses collide, they seed the galaxy with the raw materials for planets, for oceans, and for life itself. We are not just observers of this cosmic cycle, we are products of it. Our very existence is tied to the explosive deaths of these extreme objects, but the connection runs even deeper than our atomic composition. By studying how matter behaves under pressures that shred the rules, we are conducting the ultimate stress test for the laws of physics. The principles of quantum mechanics and general relativity that govern a neutron star's heart are the very same laws that dictate the flow of time, the nature of gravity, and the stability of atoms here on Earth. Probing the limits of matter in a neutron star is not an abstract exercise. It is how we confirm the rulebook for our entire universe. It satisfies a fundamental human drive to understand where we came from and what the world is truly made of, pushing the boundaries of knowledge to reveal the hidden architecture of reality itself. Our journey to the edge of physics reveals a universe far stranger than we ever dreamed. These stellar corpses are not merely cosmic curiosities. They are the ultimate crucibles, forging the elements of life in their violent hearts and deaths. They challenge every rule we have written, pushing our understanding of matter and force to the absolute breaking point. From the impossible strength of nuclear posture to the ghostly cooling of actions, every new discovery peels back a layer, exposing a deeper mystery beneath. The steady pulse of a pulsar, the silent warp of space-time, the brilliant flash of a kilonova, these are all messages in a bottle, cast across the void from a realm where the familiar laws of physics dissolve. As our telescopes grow more powerful and our detectors more sensitive, we are not just building better instruments, we are forging new keys for the locked doors at the center of these stars. The secrets waiting within are not just about the fate of dead suns. They are clues to the fundamental architecture of everything, a code written in the language of crushed neutrons and primordial quark soup. The exploration has only just begun, and each new answer promises to reveal a universe more wondrous and more mysterious than the last.